Hey everyone. So in this video we're going to be starting absolute convergence and the root and ratio test, or section 11.6 in the textbook, which is in the description. So the four main ideas, as we stated, was absolute convergence, conditional convergence, the ratio test, and the root test. So that's what we will be looking at in this video. So first we have absolute convergence, and this is, suppose we have a series a sub n. If the series of the absolute values converges, then we say that the original series is absolutely convergent. So what this means is that even if we ignore all the signs and make every term positive, the series still converges. So if a series converges absolutely, then it definitely converges. Right? Think of the word like absolutely converges, like it converges strongly, right? Like when you say you're absolute about something, you're really confident, or you're strong about something. So think about that way for this. Next we have conditional convergence. So it's the opposite basically. So let's say you have your original series converges, but the absolute value series doesn't converge, then we say that the series is conditionally convergent. So it means that the series converges only because the positive and negative terms cancel in the right way, if that makes sense. So I guess a good way to think about this is that absolute convergence, think of it as like stronger, like I said before. And for conditional convergence, think about it that as like it converges but only because of like the cancellations. Now we're going to move on to the ratio test. So the ratio test uses L equals the limit as n approaches infinity of a sub n plus 1 over a sub n. Then we have, if the L value is less than 1, the series converges absolutely. However, if L is greater than 1 or it equals infinity, we say the series diverges. And lastly, if L equals 1, the test is inconclusive. So when should we be using this test, right? So the ratio test is like a good choice when you know your term has factorials, which look like these, the exclamation mark, or you have exponentials, or you have powers like something like c to the n. Because if you think about it, when you compare like the n plus 1 terms to a sub n, they kind of simplify pretty cleanly. And we will see this more later in examples. So now for our next test, we have the root test. So the root test uses the limit as n approaches infinity of the nth radical of the absolute value of a sub n. And we also have the same conditions. So for the root test and ratio test, I guess that's a good thing. So when you memorize one, you memorize two. So you kill two birds with one stone. So the same conditions. If L is less than 1, we say the series converges absolutely. If L is greater than 1 or equal to infinity, it diverges. And if it's equal to 1, we say it's tested inconclusive. Now the only time you use this test is when your whole entire term is raised to the nth power, or the nth root, we say. The nth power, because the nth root will remove that power immediately. So I know everything kind of sounds like what is all this factorials root power, but it will make sense once we dive into the examples. But before we start, I want to just clarify really quick that for both the ratio and root test, if the limit is equal to 1, it tells us nothing. That means we need to use a different test. So if you ever get one, don't just think that, oh, that means like, I don't know, just don't write the series diverge, or we don't know, or don't write inconclusive. That means we have to use a different test to find out about the series. So now you can get started. So for first example, also ignore my writing because it's kind of impossible to write on this iPad. I don't know why, but I'm just terrible at it. But first example is determine whether the series -1 to n minus 1 over n squared is absolutely convergent, conditionally convergent, or divergent. So if you remember from last video, we have the alternator in this series, the -1 to the n minus 1. However, the question is asking if it converges absolutely, conditionally, or it's divergent. So the first thing we should try is doing the absolute value series, because we know that if the absolute value series converges, then we're done immediately because we know that the other series converges. So the first thing to do is take the absolute value of this series. So now we want to take the absolute value of this, right? So if you remember, we can also rewrite this as this way. If it helps you visualize it, sorry, the 2 looks really off. So that's another way you can rewrite this series. And that's supposed to be a multiply the dot. It kind of looks weird, but that's my fault. So when we take the absolute value of the series, you know that the -1 to the n minus 1, all it does is control the sign, right? It just bounces between positive minus, positive minus, positive minus. So the absolute value of the alternator, this part, the -1 to n minus 1, is just 1. Because all this thing is responsible for is just changing the signs. So when you take the absolute value of that, you just get 1. Therefore, the series becomes this is what we get for the series after we take the absolute value. Remember, the 1 over n squared just stays the same because there's not really any negative signs or anything, so it's just going to remain the same. But the -1 to n minus 1, all it does is just flips, changes the sign. So when you take the absolute value, it becomes 1. Now, if you want, you can plug in a few numbers, like n equals 1, 2, 3, 4, however many, and see that what you get when you take the terms without the absolute value signs, you get like what 1 over 1 squared minus 1 over 2 squared and stuff like that. But when you remove the absolute value signs, you'll just remove the sign, so it'll just be 1 over 1 squared, 1 over 2 squared, stuff like that. So when you take absolute value, it just becomes 1. So if it's hard for you to visualize it, then you can, I guess, plug in a few numbers to see that. But if you just want to memorize, just memorize that whenever you have like an alternator, the absolute value, that's just always going to be 1. So up to you. So now we took the absolute value. So now let's test the absolute value series. So we know that this series is a p series with our p value equaling 2. And we know that a p series converges. So I'll write that down. P series converges when p is greater than 1. And we know that 2 is greater than 1, so the series converges. We know that 2 is greater than 1, therefore, whoops, sorry, that does not look like a 1. So we can see the series converges. So we know that the absolute value series converges, therefore the original series is absolutely convergent. So our final answer, we can write something like this. Is absolutely convergent. And there's our answer for the first example. Now let's move to the next one. Determine whether the series -1 to n minus 1 over n is absolutely convergent, conditionally convergent, or divergent. So this is another alternating series, right? So it's kind of similar to the last one. The last one was just n squared, this one is just n. But this one is a little different, and we'll see why. So the question is asking if it converges absolutely or conditionally, or if it diverges. So for this one, well, for last example, we could see that it was n squared, right? So we knew that it was a p series. But for this one, we're not really sure, right? Because we know when p is less than or equal to 1, this diverges. So for this one, we should start by testing the original series, and then we do the absolute value series, and we compare both of those answers. Because just because we know one of them doesn't mean the other one. Remember, this could also be conditionally convergent. Maybe that the series diverges, but when you take the absolute value, sorry, yeah, maybe this one converges, this series converges, but when you take the absolute value, that one diverges. So it could be conditional. So therefore, in this example, we're going to be testing both the original series and the absolute value series. So let's test the original series. So we can rewrite this like we've been doing for every example when we have an alternator. So we know our term is just 1 over n. Remember, when we're doing the alternating series test, when you check two things. And the first step is to check whether your term is decreasing. So to do that, we also need the term plus 1, which is just equal to 1 over n plus 1. And we note that n plus 1 is bigger than n, so we take the reciprocals. 1 over n plus 1 is less than 1 over n. Therefore, we know that the fraction gets smaller. And if you want, you can plug in numbers to see that. But yeah. So now we know that our n plus 1, we know that b sub n is decreasing. So now what's the other test? Well, if you remember, the next test is to check if the limit of the term reaches 0. So now let's check. So does the limit as n approaches infinity of 1 over n equals 0? Well, we know that a small number divided by a huge number is equal to 0. We've done this like a million times. So we can say that the original alternating series converges, right? We know that the limit equals 0, and we know that the term is decreasing. So I'm going to erase this, but I'm going to keep this right here. That's the arrow where the original one converges, right? Now we're going to test the absolute value one. Now we have to take the absolute value of the series. So basically just add these. So if you remember from last example, the alternator, all it does is change the sign, right? So that's going to be equal to 1 and take the absolute value. So we just left with the series 1 over n. So if you know, this is the harmonic series, and this series diverges. So now we can conclude that we have the original series converges, but the absolute value series diverges. Therefore, our final answer is going to be is conditionally convergent. So you always want to check both series, but sometimes you can just check for the absolute value one if you want to check that first, if that one converges. Because if the absolute value one converges, then you know the original one's also going to converge. But if you wanted to, you could also take the absolute value of the series first, and you saw this diverges. Doesn't mean that the series diverges, so then you'll have to redo the first one too. But it's up to you. You can always just take the absolute value of a series first, or you can just do both. You can start with finding the original series, then the absolute value, but up to you. So we know that in this case the absolute value one diverged, but the original one converged. So if you remember from the theorem that if the original one converges but the absolute value one diverges, then this series is conditionally convergent. That's our final answer. Now we're going to be moving into our next problem. Determine whether the series n squared times 3 to the n over n factorial converges or diverges. So if you remember, or if you took notes from earlier, whenever we were going over the ratio test, I told you that the best time to use a ratio test, or you should pick a ratio test when you see a factorial or an exponential. But the biggest giveaway should be the factorial. And also, I don't know if I explained that clearly in the ratio test, but whenever I said one of them was c to the n, to look for c is just a constant to raise to a power. So in this case, c is 3 is raised to the n. I don't know if I explained that, maybe if y'all were confused, but when I said that to look for c to the n, I meant like a constant raised to the nth power. But yeah, so before we start, this one's going to be a little tricky. This is a little harder example, but we'll knock it down. It's going to be easy. So we explained why we chose the ratio test. So now let's define our term, right? So we know our term is just n squared times 3 to the n over n factorial. So now, you know, for the ratio test we need a sub n. It's and a sub n plus 1. So whenever you do the n plus 1, you're just replacing every single n with an n plus 1. So it's going to look like n plus 1 squared times 3 to the n plus 1 over n plus 1 factorial. So now we know the ratio test looks like something like this, right? It's a sub n plus 1 over a sub n, then we take the limits. So we want to form this. So now let's form that. So a sub n plus 1 was n plus, sorry, handwriting, n plus 1 squared times 3 n plus 1 over n plus 1 factorial, all of that divided by n squared 3 to the n over n factorial. Now, this is probably the hardest part of the problem. The hardest part of the problem is probably simplifying all this. It's actually not like doing it, so this is where it gets tricky. Now, for me, I don't really like doing this step. Well, what I mean by step, I mean like I don't really like dividing by the term. I always just, because we're going to end up multiplying by the reciprocal to get rid of the fraction or the denominator. So normally I just write my terms, like whenever I'm writing it, I just write the a sub n plus 1, then I just multiply it by the reciprocal, so I don't have to like write aloud like this, then just say I multiply it by this. So it just saves, like, I don't know, a few seconds, but for example I will, and you should always, so just in case you don't make a misstep and multiplying by the reciprocal. But now we know this is going to be equal to n plus 1 squared times 3 to the n plus 1 over n plus 1 factorial, all of this multiplied by n factorial over n squared times 3 to the n. Now, I'm going to make this a little bit smaller and remove this because we're going to need space. What am I doing? Can I not make this smaller? Sorry, guys, I don't know how to use this. I guess I can't make it smaller. Okay, I'll erase this on the side. Move this there. So we're going to simplify this one piece at a time. We are not going to be multiplying this whole entire expression. We're not going to be multiplying. We're just going to be like, I probably don't even know how to do that, I'm not going to lie. But luckily, with fractions, you can simplify piece by piece. So the first thing we're going to do, I'll highlight in blue really quick, is we're going to be simplifying the powers of 3 first. So see, you have a 3n plus 1 here, and then 3n on the bottom. We can simplify that. So let's go ahead and simplify these really quick. So we know that 3n plus 1 over 3n is going to be equal to 3. Now why? I'll explain right now. So 3n plus 1 can be rewritten as 3 times 3 to the n. This is over 3 to the n, right? So these two cancel out and you're left with 3. If that also didn't make sense, you can plug in a number. So let's plug in a 2, n equals 2. So 2 plus 1 on the top is 3 over 3 squared. So what's 3 cubed? Well, 3 times 3 is 9. 9 times 3 is 27. So you get 27 divided by, what's 3 squared? 9. You know, by math, 27 divided by 9 is 3. So there's like millions ways, or like this is like the top 3 ways I guess you could use to simplify or to understand why 3 to the n plus 1 over 3 to the n is 3. So you can always plug in the numbers to check or to make sure. But now we have our first one. So we simplified this, the 3's term. So let's rewrite this to the corner. We know that there's our 3 simplified. Now let's simplify the hardest thing probably. Well, not the hardest, but the most stuff people get confused on. Let's simplify this factorial. The n factorial over n plus 1 factorial now. We're going to be simplifying these two. So we're going to have n factorial over n plus 1 factorial. So if you know f factorial means you're multiplying every whole number down to 1. For example, 4 factorial just means 4 times 3 times 2 times 1. So you're multiplying by every number. You just keep going down in numbers until you reach 1. That's all a factorial is, like simplified. So in this case, so let's try 5 factorial. We know 5 factorial is just going to be 5 times 4 times 3 times 2 times 1, right? We're just multiplying every number downwards till we reach 1. So think about it this way, right? Let's look at the bottom, right? The n plus 1 factorial. We know that n plus 1 factorial is going to be equal to n plus 1 times the numbers after it, right? So like let's say you plug in a 3, right? So this is going to be 4 factorial, right? So it's going to be 4 times all the numbers after that, right? So 4 times 3 factorial, because 3 factorial is 3 times 2 times 1. But actually, let me do an example real quick to show what I'm getting at. So let's plug in a 3, right? So let's say we have 3 plus 1 factorial is also equal to, 3 plus 1 is equal to 4 factorial. And we can say 4 factorial is equal to 4 times 3 factorial, right? Because 3 factorial is just 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. So we can just write it as the next term of the factorial of the next term. That's how we can simplify this. So the same way, hopefully that confused, or not confused, sorry. Hopefully that, what's that word? That made it less complicated, there we go. As to why n plus 1 factorial can be written as that term times the remaining terms of the factorial. So now we can go ahead and rewrite this. So this is equal to n factorial over n plus 1 times n factorial. And the reason we did this is to cancel the stuff. So these two cancel, so this leaves us with 1 over n plus 1. Therefore, let's erase this and rewrite this as we simplified this to, this is equal to 1 over n plus 1. So now, let's move this also to the top. Now, we can rewrite this. So the ratio is going to become, so right equals here. So we still have the n plus 1 squared. We didn't touch that. We can rewrite this as over n squared. We didn't touch the n squared. N plus 1 squared over n squared. All of this is multiplied by 3. Remember, this was equal to 3. And all of that is multiplied by 1 over n plus 1. So now the only thing left we have to do is to simplify the n plus 1 squared and the n squared somehow. Now, if you can see, we have an n plus, in blue, we have an n plus 1 squared here, we have an n plus 1 right here. So one of the terms can cancel out. So we can simplify this. Oops. We can simplify this further by saying this is just plus 1. Remember, only one of the terms cancel out. Over n squared. Times 3 times 1 over n plus 1. Well, we know 3 times 1 is, we can just rewrite this side. The 3 times 1 over n plus 1 is just 3 over n plus 1. Wait. I'm sorry. I just messed up. That's just multiplied by 3. Because we canceled out the n plus 1 here. From right here and right here. Whoops. See, this is really confusing when you're not organized like... Sorry, when you're not organized, and unfortunately, when I do math, I'm terrible at organization. So the simplification, our final simplification should be, let's put the 3 in front. 3 times, we had 1 factor from n plus 1. We canceled out n plus 1 here, so it'll just be 3 times n plus 1 over n squared, I think. And yeah. So I'm sorry if this is confusing, but maybe hopefully you're better organizing than me. But basically, when you get to this step, before we move on, let me explain really quick. So I box it in blue. Whenever you get to this step, right, find common terms you can like simplify. So for example, we saw there was a 3n plus 1 here and 3n. You can just take those two aside and simplify those. Then as we saw, we had 2 factorials, n factorial, n plus 1 factorial. We simplified that. Then I saw that there was an n plus 1 on one of the answers that we simplified, and there was an n plus 1 here. So we could take out a term. So basically all you want to do is you want to manipulate ways to find things to simplify. That's the hardest part of this test, or whenever you're going to use this test. This is going to, whenever like you have terms like that are messy like this, that's going to be the hardest part, is you just want to find things to simplify. So the best thing to do is look for common terms and get those out of the way and simplify those. Simplify the easiest ones that you can. So now we can go ahead and take the limit of this. So I'm going to erase all this. So if you want to take a second and write this down. So now let's move this up. So this was our final answer, or simplified term, my bad, I meant. So now we need to take the limit. So we have the limit as n approaching infinity of 3 times n plus 1 over n squared. There. So before we take the limit, let's rewrite these fractions. If you know, we can split this fraction. So this is equal to 3 times n divided by n squared is just 1 over n. Because remember, this is n to the first power imaginary 1. And when you divide by like exponential, they subtract. So 1 minus 2 is negative 1. And you can rewrite as n negative 1 as just 1 over n. So that's where I got the 1 over n from. So 3 times 1 over n plus, whoops, and then this is just 1 over n squared. So let's rewrite this. The limit is n approaching infinity of 3 times 1 over n plus 1 over n squared is equal to 1 over infinity is just 0, plus 1 over infinity squared is also just 0. Remember, a small number divided by a big number is 0. And 3 times 0, everything is just 0. So we know that 0 is less than 1. So this series, or you can just write this notation right here, n equals 1 to infinity of n squared times 3 to the n over n factorial converges absolutely by the ratio test. Now, you didn't have to do a simplification if you know. When you do use the limit to infinity, you know that there was an n squared at the bottom, right? So you know that's whenever you have a bigger number or like a higher power on the bottom, it's always going to be equal to 0 when you take the limit. Like bigger on bottom means limit goes 0. That's how I learned it. But I simplified it for you guys, so hopefully it makes sense that y algebraically equals to 0. So we know that, and then we got it's equal to 0, so we know that one of the conditions was that if L was less than 1, the series converges absolutely. So that's what we did. So hopefully this example wasn't too challenging, and hopefully it wasn't too confusing by the way I was writing it, but basically it's just you want to simplify terms you know you can, or like common terms that look alike. Try simplifying those, then simplify as much as you can and just take the limit. And you can determine based on what you get. So now, let's go to this problem. We have determine what of the series 2n plus 1 over 3n plus 4 to the nth power converges or diverges. So if we go back, I want to go back really quick to, where was it? Right here, the root test. This is what I meant when I said when to use, when I said the whole term is raised to the nth power. As you can see, this whole entire term is raised to the nth power. Whoops, I just erased that. But this whole term is going to be raised to the nth power, so we can use the root test to simplify this. So the algebra becomes simpler. So the first thing we want to do is let's just write the term down. It's just 2n plus 1 over 3n plus 4 to the nth power. So the root test asks us to take the nth root of this. So the term is already positive, right? So the absolute value doesn't matter. So we don't really need to take it, because when you take the absolute value of the term, we're going to get the same thing, 2n plus 1 over 3n plus 4 to the nth power. Therefore, we can take the nth root, so this is going to be this kind of looks cool. I don't know, just writing like that, like it looks pretty cool. So the n and the n cancel, so we're left with 2n plus 1 over 3n plus 4 So if this is confusing why the n and n cancel out, like think of like examples like this, right? Like let's say you took the cube roots of, I don't know, 2/3 cubed. You know, square root and the exponents cancel out, right? So this would just be equal to 2/3. So same idea here. We had it raised to the nth power, so we take the nth root to cancel out the nth power. That's a lot of n's in one sentence. So now we did that, right? So now all that's left to do is just to take the limits. So the limit is n approaching infinity of 2n plus 1 over 3n plus 4. So we can just divide both terms by n. So it's equal to 2. Remember, 2n divided by n is just 2 plus 1 over n over, remember, 3n divided by n is just 3 plus 4 over n. Now we can take that as an approaching infinity. So you know that 1 over infinity is just 0, 4 over infinity is just 0. So it's going to be 2 plus 0 over 3 plus 0, which is equal to 2/3. Well, that's crazy. The example I did earlier to show the cancels was also 2/3. What a coincidence. So, anyways, we know that L is equal to 2/3, And we know 2/3 is equal to 0.67, ironically 67. And we know that 0.67 is less than 1. Therefore, we can say that the corner right here equals 1 to infinity. So what is this going to be? What's the answer? I'll give you like 2 seconds to think while I write the series down. If you said this series converges conditionally, you are wrong. This one doesn't even ask for conditionally convergence. But this one converges absolutely. By the root test. So the root test is pretty easy. Some of them may look gross, like you might have like, I don't know, 5 to the n over like 3 to the n, or maybe like some random stuff. But if you see like the whole term is raised to the n power, that's like the biggest indicator. You should go straight to the root test. No other test, just the root test. And so hopefully this wasn't too confusing. Now let's do a recap really quick. So we know a series is absolutely convergent if, when you take the absolute value of that series, it converges. Duh. And then we know a series is conditionally convergent if the original series converges, but the absolute value series diverges. And we know that the ratio test is best for factorials and exponentials, like c to the n. And then the root test is used best for when the whole entire term is raised to the nth power. And lastly, for both tests, same conditions. If your L value is less than 1, it absolutely converges. If it's greater than 1 or infinity, it diverges. And if it's equal to 1, we have to use a new test because this one failed us. We're a failure then if it equals 1, I guess. Well, hopefully that helped you, and have a good day.